Script example 1 for students is the one that you're going to complete. Script example 1 is the solution set. And that's what I'm going to lead you through. So let's go straight into it. If something in R has a hashtag in front of it, and I'm old enough to remember when this was just a number sign, if it has a hashtag in front of it, it is a comment. R will not recognize it as anything other than a comment. So we can see this down here in the console. If I say x is 5, it now assigns it as x. Now, if I hash something out and say that y is 6, and I try and say what y is, it doesn't know what y is, because if we look over here in the environment, y is not here, because we commented it out. So it's good to be able to define out and tell the user what is going on. So this is usually where you put your header in. You put your name and your affiliation in to take credit for the code. And then you basically give a synopsis of what it's trying to do. This header is not complete, but it's just an example. So that's what these hashtags mean. It's just saying that that's a comment, and R won't recognize it as anything other than a comment. So the first step that we want to do is we want to bring data in so that we can now start building out the rest of what the code is trying to do. So data_1 is equal to, or is being assigned, something that's read from a CSV. So you want to read a CSV file that is Hornick et al. 1971 human1.csv. The .csv has to be there, or else R won't recognize this as a .csv file. And because it's a string, it has to be in quotes. Again, always use double quotes just for safety's sake, because some of these packages are quite old. The comma separates the next command that's going to go into this function itself, and it's saying that there's going to be a header to the data. So first, what I'm going to do is I'm going to set my working directory to the source file location so that I can actually grab the data that's in there. So what we'll see is once I do that, it prints down here set working directory, and then my working directory to get to the file itself, or the folder location itself. Now, if what I want to do, I can highlight this, and I can run just this one selection. So just run the current line. I run that, and no errors come out, meaning that it was able to find the file, it was able to read it in, and now if I put in data_1, I can see it there. Now, if you have a lot of data, it's going to fill up your console, and it's going to be hard to see what's happening. So you want to check to make sure that your headers came in. You want to check to make sure that all the values that you're expecting have come in, and that what's supposed to be a number is a number, and it's something that can be recognized by R. If you have a lot of data, though, capital V view, and then whatever the data frame, vector, or matrix it is that you want to look at, in parentheses, will open up a new window here that's going to be easier for you to scroll through. So if I had 100 or 10,000 or a million data points in here, I can now actually just scroll up and down as though you would in any other window to be able to see if everything loaded in properly, and that's something that you're going to be able to use. Check again to see that the headers are actually in there, and you're going to have to be case specific. So if it's uppercase P, you always have to use the uppercase. It won't be able to parse that out unless you do that. So that view command will work even in just the R base GUI, and in RStudio, that's how it pops up here as well. So that's reading the data in. First step is we want to simulate a dose set with the same number of doses in the Hornick data. So what we're saying is we want to get the same number of doses, and we want to simulate something that's going to be similar to the doses that are in that data. So what I'm doing here is I'm saying that some vector is going to be filled with the simulated data. D range could be named anything else. You can name it whatever you want. You can name it X or anything else, but dose range is telling me that there's a range of doses that I'm simulating. So the reason that you're going to see this parsing, or this syntax here, is very specific. RUnif is a random uniform distribution. So if I do help RUnif, I see what it's going to be expecting. So I look down here, random or RUnif, and I can come down and see what it's going to be expecting coming through. You can go through the rest of the help file, and you're going to be able to say DUnif is giving me the density. RUnif is going to give me random variates off of the uniform distribution. A uniform distribution would be preferred for something like this because you are assigning equal probabilities essentially to an occurrence happening. So if I set my seed and I say that X is a random uniform distribution, I want to make 10 values, and I want to say that the minimum is 2 and the maximum is 10. It'll give me 10 values. If I look at what X looks like, it'll give me 10 values that are between 2 and 10. But they all have equal probabilities of occurring in their output. So I can make a histogram of that and see what it looks like. And so there's higher frequency of specific sets of values, but the idea of the uniform distribution is that you're not assigning any additional complexity to, the model itself. It's just a uniform distribution of events that can happen. So I'm saying that it's a random uniform variates that come out of it. Length, data 1, dose. So remember, data 1 is the data that we brought in, and if we look at what length is doing, make sure I spell it right. So if we do length data 1, it's going to tell me that it's 4. Now, that's because we're saying that for the entire data set in data 1, what's the length of it? And so it's going to give me all the rows. There are 4 columns. There are 4 columns in the data_1 data file, or variable that got brought into R. But we want to know how many dose values there are in this. So we need to be specific about that. So data1 $dose will say, look at just the dose column in the data1 file. That's telling me that there are 7 rows or 7 dose values within the data1 data set that we have brought in. So if we look back at the syntax of what the random uniform is doing, is it's saying I want 10 random variates between 2 and 10. So I want 7 random variates because the length of the dose column, or the number of rows in the dose column, is 7. Now you could have pulled out what the number is and then just put 7 in here, but then if you change your data, you would have to change this command again, and any other command that would need to know the length of the dose column or the number of doses in the data would have to be changed as well. So specifying it as length of the dose data is going to make it more adaptable and something that can be used for other purposes and used as you change things or bring other data in. It makes it much more adaptable. Same basic concept. What I'm saying here now is, so remember the syntax. Random uniform variate, 10 values out, minimum of 2, maximum of 10. So I want the minimum of the doses coming through. So if we look through here, the minimum should be 1 times 10 to the 4. So if I do minimum data1 $dose, it should be 1 times 10 to the 4, or 10,000. So I want the minimum, then I want the maximum, and then so that's why we have max data1 $dose. The important things to remember here are that you're developing a random uniform distribution and you're taking random variates from a uniform distribution. You want it to be adaptable, so you're going to do the length of the dose column, or the number of doses that are in the data set itself, for the total amount of random variates that come out, minimum of the doses and maximum of the doses. This syntax makes it much more adaptable and something that if you change your data, you don't have to change the rest of your code. So that's why it's important to understand how this syntax is working. So that'll be the solution to number 1, simulate a dose set with the same number of doses in the Hornick data. Number 2, calculate the observed positive response probability, or OPOS, using the Hornick data. So in this case, I'm actually telling you what to name the vector. So what you need to do is now say, I'm going to make a new vector, and I'm going to assign it something else. And again, My old ways have caught up with me, so we're going to change that to the more appropriate modern use of the less than dash meaning equals. So the vector opos is going to be equal to data1 positive response. So each one of these positive responses divided by each one of these total numbers. So if we're thinking about the observed probability of response, it's a positive response is what we're looking for, whether or not the person got sick, and out of the total number of people who were there. So in this case, we're doing 0 divided by 2, 0 divided by 4, 0 divided by 4, 2 divided by 4, and on for the rest of it. So if we think back to how we had those examples for the matrices, if I don't specify a specific row and column, it's going to multiply or divide another value by everything in that data set. So what I'm saying here is just the positive response column divided by the total number column. And so what it'll do is each individual point in here, so it will go row by row, dividing the row 1, column 2 by row 1, column 4, and then on down the line. It'll fill that opos vector, and then we move on. So let me run this one since I didn't run it. So again, if you want to run a single line, you highlight it and click Run. So now we have drange brought in, and if we want to view it, we can either double click it here. Oh, it's not. Oh, it's not. Oh, okay. Because it's a value and not data, we can't click it. So if it's data, we can just click it, and it'll make the view command pop up down here in the console and pop up this view. But because it's a value, what we want to do, if we want to look at it, is actually type it in by hand. This header that pops out, if you need to export this data in some way for any other purpose, then you're going to have to change this around, but we won't get to that until we get to the risk characterization, because that'll be when it becomes more important to understand that. So hold tight on what this header is actually saying. It's just a little quirk with R on that case. Now, one thing that most of you probably have noticed already is that I did not set my seed. So that's one error that's in here that was meant to be an error that you would catch. But since I'm doing this video, I will help you catch it. So set.seed, and since we're using RStudio, it says, oh, I think you're trying to set a seed. So you put that in, and then you can put in whatever number you want. So I'll put in just some random value. And then we can see, we can run it again to get the values that we want based on that seed. We're not doing any kind of random sampling here, so we don't have to reset a seed or do anything like that. So we'll run this, and what we'll see is that it is now giving me probabilities of some response. So if we look back to what that data actually looks like, so if we do data 1, we should be seeing 50% probabilities of response for anything other than a 0 here, because we have 2 and a 4, a 1 and a 2, and a 1 and a 2. And so that's what we're seeing, 0, 0, 0, 0.5, 0.5, 0, 0.5. So we're seeing something that actually makes sense. Now, if you're having a lot of data, you can't go through row by row like that. So what you'll do to verify what your code is doing is pick specific values and make sure that it's predicting what you're expecting it to predict or calculating what you expect it to calculate. But that's just a good check to have as you go through this kind of modeling. So, number 3, calculate your summary statistics. I'm telling you what to use. Summary, open close parenthesis, is a function specific to R that will take a summary of what is in your data. So, what we can do is we can break it out to make sure that we are getting exactly what we want. So we're saying that we want the summary statistics, a plot, and a histogram in a single window for data 1, doses, drange, and opos. So data 1 doses means that we just want the doses column, summary, plot, and histogram, and drange and opos are single vectors, so we don't have to try and parse anything out by way of that data. So we'll say summary, data 1, $ doses. $ again, remember, is defining the dose column within the data1 data. The semicolon here is saying this has been a command. A new command is about to start within this same line. Put the space in just so people can read it easier. Summary, derange. Again, we don't have to specify any part of this vector. We want to take the summary of the whole vector. Then we have another semicolon that says this function is now done. I'm done putting anything into this function here. New command on the same line, summary, pause. What that's going to do is it's going to give us a set of summaries. So we'll highlight it, we'll click run to get out what we want. So it is a little messy, but remember, you just read it from left to right, top to bottom. So you started here as summary data1 dose. So this would be the summary of data1 dose. So it's a minimum, maximum, first quartile, median, mean, and third quartile. Pull out the values that you're interested in, but in this case, you just want to be able to show that you have the summaries getting popped out. If you get errors in here, it's probably because you have misspelled something, or a vector was not built, or you deleted it along the way somehow, but that's typically where you run into it, is usually spelling errors in something like this. So now the next part of it, we want to make a plot and a histogram in a single window for each of these. So we want to make a new device window. So X11 will work on Windows, Macs, and Linux. In some cases, Mac users, you may need to install your X11 device. If you run into that, where it's giving you an error that your X11 device or your X11 server is not installed properly, let me know and we can walk through that next week to be able to make sure that you have that. If Mac users only, if X11 is not working for you and you can't install it on your own, use Quartz. In a Mac, because I'm using a Mac right now, if I do Quartz, open close parenthesis, it opens up a device window exactly the same as an X11 would do. X11, and there we go. So you see how that works? Let me find what I want. There we go. So Quartz and X11 are doing the same thing in Mac. Windows users, this is one of the times that you win. X11, I have never seen not work on Windows. If that is the case where you do run into that, your special command for Windows is Windows. Oop. No, not Windows. Sorry. Oh, they must have removed it. Well, sorry, PC users, they're assuming that you have X11 working. But again, I've never run into it where X11 doesn't work on a Windows machine. Oh, it's not working because I'm not running a Windows machine. That makes sense. Sorry. So X11 will open up a new device window. And remember, I'm now going to parameterize this X11 window by saying I'm going to want 3 rows for plots and 2 columns for plots. So remember, we have 3 different data type or data sets that we want to make a plot and a histogram for. So if we line them out where we have plot the dose, give me a histogram of the dose, plot the range, give me a histogram of the range, plot the positive, pause, give me a histogram of the positives. Remember how that's filling out. We are going from left to right, top to bottom. So it'll be the same, it'll be a plot of the dose and a histogram of the dose right next to each other so you can make comparisons. So remember, so this is what this is doing. There's a review. Open up a new X11 device window to put a plot into it. Reparameterize that device window to be able to have 3 rows and 2 columns, and then start filling the rows and columns here. Again, semicolon is just saying I made an X11 command, that command is over, new command on this line, and then on from there. It just makes things simpler. It makes it that you don't have so many lines of code that you're writing. So what we'll do is we'll open up the X11 and then make a parameterized, reparameterize the plot window, and then plot is for making a plot of the doses, histogram is hist, and then on for the rest of them. So we've already run the summary, let's run the X11 command and then the plotting, run that line, the X11 window will pop up, and then we'll be able to see, and hopefully it's not just capturing the one RStudio screen, but also the X11 here. So what we see is an index and then the doses, and then an index and then the D range, and an index and O pause. And remember, with the histogram, it has more specific titling, so O pause and frequency, D range and frequency, dose and frequency. As you can see, this is actually fairly small, so if one thing that you wanted to do is you wanted to change it so that you could actually see it a bit better, you could put in 600 by 400 for your X11 window, and then run it, and now you have a much bigger image that just goes off the screen because I'm using a separate monitor. So the pixel sizes are different from a standard screen. So keeping it just as normal, we can plot that again, run, and now we have the graphics that we wanted to. So you're not going to have to do anything by way of saving that, so you can just exit out of that after you check to make sure it's actually plotting things and making histograms as you would expect. So now you want to save this plot as a PNG file. So remember, everything's getting saved to my current working directory. So I want to double check that it's going to go where I'm expecting it. Get WD, open close parentheses, tells me that I'm in my Lecture 3 folder, which is where I want it to go. If you wanted to change your destination on the fly, you can do that. But let's first go through and talk about the syntax here. I'm going to make a new PNG image. I'm going to call it testplots.png. Now, the PNG command will not typically give you a problem if you don't define the size of the screen that you want to use. It'll just go to the default size screen like you saw when we ran this X11 command. So it's a fairly default size screen, and the resolution is usually pretty good when you're looking at that. We want the exact same plots, so all we're really doing is cutting out this X11 command. What would happen is you're opening a device window in which to make a plot. Then you're going to open a different device window to make a plot, and it's going to give you an error. It's basically going to say, I don't know where to put this plot, or worse, it'll just put it in the X11 window, and you'll assume that it went to your PNG, move on, and you won't have that image. So really what we're doing is we're just deleting this portion of the plotting line because we want the exact same plot. We want it to be parameterized to have 3 rows and 2 columns and the exact same plot layout, and then turn off the device, which means save the file. So if we look at my files currently, I have all these other images that are not actual images at all, or images that we care about, but you can see here my script examples as well as the data here. So this is where my working directory is, and this is where we're going to be able to actually see things as they pop up. So what I'll do is I'll highlight all of it and then click Run, and it pops up. Test plots, open it up. It opens it up as a PNG file, and now I can see what my plots look like. So now what this is saved specifically within my files in my working directory, and I can do with it as I wish. I can, in my Finder, I can open it up in Photoshop or GIMP Shop, which is a free version of Photoshop, and manipulate the image if I wish. Change the background color or make the lines darker or something along those lines. Be very, very careful how you use Photoshop on your images, only to enhance the quality of the lines or the colors or something along those lines. You can change any of the coloration of your plots within R, but the risk with Photoshop is that it will be a legacy of that this was a photoshopped file. So typically what I do is I just use that to save it as an encapsulated PostScript or some other specific file. That's an aside. So, but now what you have is you have a file that you can transfer around, email to people, and use as you need it. So again, open up a new PNG that you're going to plot into, name it testplots.png. Again, this has to be in quotes because it is a string. Otherwise, R won't know what you're talking about. So make a PNG, name it testplots.png, or whatever you want to name it. You can name it whatever you want. Parameterize the plotting window to have 3 rows and 2 columns. Put these plots in that go from left to right, top to bottom as it fills the plot window, and then turn off the device. So what I can do is if I comment this out, and let's say that I want to call this something else, so testplots2.png. If I run this, now keep your eye down here. If it comes in, it'll be testplots_2.png, and it should be under here. If I run this, it doesn't show up. Now there was about a 1 second lag before, but this is taking far too long. And if I'm trying to find testplots2, I'm not going to know where it is. Easiest thing to do is in your console, dev.off, which means turn off the device, which tells it to save the plot, and now it popped up. So what I'll do is I'll uncomment this so that we can use it again, and delete this file. So that disappeared from there. Run it again with the dev.off turned on, and there it is. We can open it up, and it looks exact, or just test plots because it's the exact same plots. So we go on to question 5. Generate a set of random deviates from the uniform distribution to simulate the dose range with the same number of doses. Call it D range 2, and then model the likelihood of response if the exponential k is 5 times t times 10 to the negative 11. If we had gotten into the dose response section, then you would know what the exponential model is. The exponential model is just this: 1 minus e to the negative k times d. It looks weird typed out in R, just because that's how the syntax is. It's syntax rather than just an equation. So let's go through this. So what we want to do is we want to generate a set of random deviates, and at the same time that we're generating those random deviates, we want to model something. And I'm old school. I use loops for everything. There are ways of vectorizing your code, meaning that instead of using a loop, you use an embedded function. But for loops and if loops and things like that make it more tractable for old guys like me. Let's just put it that way. So that's how I have it in. So in here again, my legacy of equal sign has reared its ugly head again. So iterations, you can name it whatever you want, but that's the number of iterations that are going to occur, so I name it iterations or iter or something like that so I can keep track of it. So iterations is equal to the length of data_1 $dose. I won't reiterate what this is. If you want, go back, but hopefully you remember what the $sign is doing there. I'm going to define PR as a matrix with the total number of rows being the number of iterations and 1 column. I know that PR, being the probability of my risk, is only going to have 1 value per dose. And so if I'm making it the number of iterations the length or the total number of doses, I want it to be able to calculate a risk for each one of those doses. So I'm going to say that the total number of rows is the total number of iterations, because I had the total number of iterations based on the total number of doses. And then 1 column, because there's only going to be 1 risk value for each dose. Now what I'm going to do is I'm going to say D range 2, because I already have a D range, and I want to name it something else. And I'm going to say the D range 2 is a matrix of total number of iterations or the total number of doses and 1 column. Now, for the sake of consistency, this should still have a seed set separately. I've already set my seed. I set my seed up here as 34. For the sake of completeness, what I should do is I should have another set seed statement here. So let's make it a different seed. And again, you can use whatever you want as long as it's a number. So I'll set my seed again, because now what I'm going to do is I'm going to simulate the dose ranges. So again, I want the same number of doses as I did before, so the total number of iterations is the total number of doses, and only 1 dose per iteration. So for I in 1, 2, the colon means 1, 2 iterations. So from 1 to the total number of iterations, I is going to iterate, and it's going to start from 1. That's what that's saying. So I is going to start at 1, and it's going to calculate something, and it's going to save that information. And then it's going to iterate to 2, calculate something, save that information, and on until you reach the end of the length of iterations. So let's just run this one, and that should be 7. So we have 7 as we would expect. So this is going to run 7 times. In the case of your Monte Carlo models, your iterations will be defined as whatever you want them to be. Nothing less than 10,000, probably nothing more than 1,000,000, or else it's going to take forever. So for I in 1, 2, the total number of iterations, I'm going to do everything that's between these curly braces. This is just standard syntax for a for loop, and it would be expected for anyone reading your code that it would be in that syntax. So anything within these curly braces, do that as long as you're able to iterate I. So from 1 to 7, do something in here. So for each ith iteration, I want to fill the ith value of d range 2 with a random uniform random variate from the uniform distribution that has the same characteristics as my dose data. In this case, I only want one value because I am only doing this per iteration, do something at each iteration. That's what I'm trying to define it as. So you still have to define the total number of random variates to generate. I only want one random variate because I'm doing this as an iterative process in my for loop. So we'll generate one random variate from the normal distribution. I want it to have the same characteristics as the dose data in the original data. So that's where this same syntax comes in as previously. This is the trick within this one here, is getting the 1 in there and making sure that you're only generating one value for each iteration. So when I fill the ith value of d range 2, so let's just make a d range 2 matrix. And if we look at what d range 2 looks like, it's empty. So when we start iterating this, at I equals 1, it will fill the first row of my d range 2 vector. In this case, it's a matrix, because that's how I defined it. But it's a single column matrix, so it's technically a vector. Anyway, I want the ith value to be filled, and so on the first iteration, it'll fill the first row. On the second iteration, it'll fill the second row and not delete the first row. There are options to make it forget its previous point, but unless you define those options, it will remember everything that it did previously, so don't worry about that. So the ith value, I fill it with a random variate from the uniform distribution. Then I want to calculate at each iteration a probability of the risk using the exponential function. So the ith value of the PR matrix is going to be filled with the exponential dose response model. And again, my old ways are catching up with me. And so 1 minus e to the. So e is the anti-log of a natural logarithm. And typically when you write it out, it is the letter e and then an exponent next to it. But in R, exp exp is the statement to be able to take the exponential of a number or a function or something else. So 1 minus e to the negative k, because I said that the k was going to be 1 times 5 to the negative, or 5 times 10 to the negative 11. So 1 minus k times the dose. I'm simulating the dose out, and so I want the ith value of the dose to calculate the ith value of the risk. So if we make this matrix real quick, again we're going to see the same thing. The PR matrix is going to be empty, and so at our iteration 1, it's going to take the ith value, or so at iteration 1, it'll take the first row of the dose, calculate the risk, and fill it in here. Second iteration, it'll take the second value of dose and fill it in here. So, obviously, if I had these lines reversed, where this line came before D range 2, R would tell me, I don't know what D range 2 is, error out, and stop running the process. So you have to remember that whichever function or other variable or vector that you're going to be filling, if it's dependent on something else, that thing that it's dependent on has to come before it. So this probability of risk is dependent on our D range 2 ith value. And so the D range 2 ith value has to be filled before we fill the probability of risk. So if we run this entire loop, and we have to run it from the end hashtag to the very beginning of the statement itself, look down here in our console, we didn't get any errors. We can look and see what D range 2 is, and it filled properly. And then we want to see what our probability of risk is, and it filled properly. So if we think about it, we're talking about something that is really quite infectious, and we're talking about humongous doses in this case, so our risks should be really quite high. So that does make sense. So now what we want to do is move on. Save a plot and histogram in this order. D range 2 to PR, PR and D range 2. Thus one plot image with one plot and 3 histograms. Have sorry about my errors. Have this saved as a JPEG file in your working directory with a height of 400 pixels and a width of 400 pixels. So I have not, height of 400 pixels and a width of 600 pixels. Sorry. So what I want to do is I want to do the same function call that I came up here. So in this case I want a PNG up here. Down here I want a JPEG. So I want to make a JPEG. I want to call it testjpeg.jpg. I want to make it 600 pixels wide and 400 pixel width high. So remember, X, Y, or row, column is how this syntax is going. I want to parameterize it. I want 1 row and 3 columns because I want to be able to compare things. Because I'm going to have 1 plot and then 3 1 plot and 2 histograms. Sorry about that again. So I want to make the JPEG, I want to call it something, and again this has to be within quotes or else R is not going to know what you're talking about. Width, height, and that's how that syntax goes. Parameterize it with 1 row and 3 columns. Fill the first row with, fill the first column with the plot, second column with the histogram of my risk, third column with the histogram of my range. Turn off the device so it'll actually save it, and we'll run it. Go back over to our files to see where it is. Testjpeg.jpg, and there we go. So once we get in a little bit more detail about the more nuanced pieces of R, we'll be able to see how we can change the X and Y axis labels, the plot title, the color and size of the plotting images themselves. But we're not there right now. So now what we want to do is we want to start changing around some of the other parameters. So what we're doing is we're trying to amplify our axis labels. So this isn't a task within the actual script itself. So we look back at the script example. All we're being asked to is generate these plots that that we're being asked for. But if we look back at this particular plot, these axes titles are very, very difficult to read. So what we're doing in this step is just an example of the other parameters that you can put into your plotting parameterization. So test JPEG underscore 2.jpg is what I'm going to call this next JPEG. I again want it to be 600 wide by 400 high. Now I'm going to parameterize it with the same number of rows and columns. 1 row, 3 columns. This is an amplifier. Please do not ask me why it's named CEX. I really don't know why. But it's an amplifier of where you're starting from. So you're setting it as a datum or a base level of, now you're going to multiply the label characters by this. So it is a value of 1. So we're saying that it's starting at 1. And we're going to amplify the label size. So if we look back here, we're going to amplify the label size. The label is this piece right here. This is the actual title of it's these pieces here. Sorry. So the labels are the values that are on the axis itself. So we want to amplify them so they're easier to see by a factor of 1.3 from our baseline. We're going to change our axis amplification by 1.2. And I'm sorry, I got that a little mixed up. So cex.lab is the label. cex.axis is the axis. So the label is going to be increased by a factor of 1.3 from the datum, and the axis is going to be increased by a factor of 1.2 from the datum. I'm now going to also change the amplification of my main. My main is my main title. So I'm going to change that amplification by a factor of 1 from the datum, 1.1 from the datum. You only want to do little incremental changes because the amplification can be quite large on a histogram or on a JPEG. So in this case, I also missed a bit of syntax. So what we're showing here is we're plotting our drange 2 to our probability of risk, so dose to risk. Our main title is risk plot. So we look back here, main title here is risk plot. We want to label our x-axis label as dose. Remember, these are strings, so we have to make sure that they're in quotes. So our x label is going to be dose, and then our y label is going to be risk of illness. So x lab is x label, y lab is y label. All of them are going to be strings, and so you put them in there. You can put special characters like Greek symbols in. We will get to that as we go farther on into the class. For right now, everything's just going to be a string as we title it. The histogram, I'm going to make a histogram of my probability of risk. I'm going to title it risk of illness rather than whatever it would now name itself, and then put as the x label risk. So our risk is down here on the x-axis, and the number of times that we encountered that risk is on our y-axis. Same thing for the histogram for the drange 2. Simulated doses is going to be the main title here, and dose is going to be the x-axis label there. So what we should see when we run all of this, test jpeg2.jpg popping up, and then let's compare it to test jpeg, the original one. So as we can see, we increased the overall size of the main titles. They're easier to read. We've increased our Y labels and our X labels. They're much easier to read. And we've increased our X-axis value numbers, so they're easier to read. So by comparing these two together, we're able to actually read this a lot better than the one on the right. So that's what we're doing on that extra parameterization there. If you are interested in doing that for any of your other plots, you can probably just cut and paste this and use it no matter what. You can play around with it as well. So you boost this up to, let's boost this up to 2 and run it again. If we open this again, now we see oversized titles. So you see how that works? So let's put this back to 1.1. I close that window so we're fine. So if I try and run this, it'll work. If I leave this device open, if I leave this window open and I try and run it again, it should throw me an error unless RS fixed it. Actually, it's because it's on a Mac, yes. So Macintosh, you can still do that. Windows users, make sure that before you try and make a JPEG that would overwrite this file, that you close this window. Otherwise, what's going to happen is R is probably going to give you an error because Windows file systems won't allow for live updating of a file that is already open. In Windows the Windows OS, you have to close a file before you can update that file, or else it throws you an error. Macintosh has something that's kind of like a live updating file structure, so you can get around that. Linux is similar as well, but not all distros of Linux have the same capabilities. Alright, so now the last one. When all of this is complete, source the complete code and track the outputs are correct and being saved to the correct location. Then source the code again, but track the time it takes for the code to source completely. So what I'll do is I will delete these plots, because those are what's going to pop out, and I want to see if it's going to source. And once you've made all of your edits, if you're in RStudio, it's going to be right up here that you haven't saved, so we'll save. So saving, so let me make a little difference. So saving would either be, if you're on Windows, hold down the Control button and press S, or click the disk, just like on Word or something else, and that will save it. If you're a Mac user, you're still going to have this little symbol, but you're going to be Command key S, and that will save it for you. To source the file, you have to be within the working directory where the file is. You have to be in a working directory where you're going to want those images to be saved, and you're going to have to be in a working directory for where the data is here. So what I'll do is I will remove all of these variables from my environment by cleaning up my environment here, and then I'm going to source the code. What sourcing the code does is it runs everything line by line all the way through. So it will read from here and on. If there is an error here, nothing below, so if there's an error in line 13, nothing below line 13 will run. It will run to this point, throw you the error, and then essentially at that point it would have only just pulled in the data. If it was error-free until line 29, it will have run everything until line 29, and then once it reached the error on line 29, it would have exited out. So that's one thing to keep in mind as well. But it ran everything through. I got no errors down here in my console that I can see. An X11 window popped out. I'm quite happy with that, but I'll close it out. And I have my plots back of test JPEG 2, and test plots.png. So that's how we source the code. On RStudio, very, very easy. Just click source and it'll run through. Now, what you'll notice is once we click source, this command popped up, which is source, and then in single quotes, and sometimes it'll be in double quotes on Windows, but mostly it'll be in single, the file path name, so the path name to the file, and then the file name itself. So you can type that in by hand if you wanted to. Now the value of learning how to do that is you can time your code. So the only reason you would want to do that is if I'm asking you or if you're really curious about it. So I want a system.time sourcing a file, and I need to now find the path. So I'll start typing it in. Actually, instead of typing it in, I'm just going to copy it from here. So it ran through all the code again, popped out my X11 window that I don't need, updated these so I can see that this is now an updated timestamp of when these files were saved. But what it's telling me is that it had took 0.026 seconds for me to run this code. The only reason you would want to do that is if you're at some point where you have the code running, but you want to make sure that it's running as optimally as possible. You're processing a lot of data and you want to see how long it takes, and then compare that to running something in parallel and make that comparison. That's really only just something to look at for your own sake. What you can also do, because you're in the working directory that you're already in, you can just do this system.time statement, and it's in the same working directory, so it'll just say look in the working directory where I currently already am, and then run the code. In this case, it took now 0.029 seconds for it to run. So I think right now what we're done on is we're done parsing through all this in the video. What I want you to do now is, after watching the video, read through this script example code again, and what I'll do is I'll update these files in Blackboard so that you can see this set.seed and everything, those little errors that I caught. Read through it and make your own notations on what the syntax is saying. And then if you want, come back and look at the video and say, did I get it? Does it match with what I was saying? And then try and replicate it. If you feel comfortable already trying to replicate it, then just go ahead and do that. But please feel free to refer back to this video as often as you need to, as well as